Good day everyone. We are second year electronics engineering students from Mondian Aura College. I am Michelle Bexon.
And I am Nika Manalili.
And I am Mylene Jada Alias, and today we will be presenting our light detecting comparator circuit.
We will discuss its component, functions, and its overall performance.
And we will also demonstrate its functionality along with the boost voltages of the circuit under varying conditions.
Once again, good day. This is Mylene Dacalios, and in this video we aim to obtain the following learning outcomes. One is identify the components of the light detecting comparator circuit and state the operation of each. 2 is calculate the induced voltage across the light detecting comparator circuit. 3. Showcase the functionality of the light detecting comparator circuit. Before anything else, what is a comparator circuit? According to Renesas, a comparator circuit compares two voltages and outputs either a 1, the voltage at the plus side, or a 0, the voltage at the negative side, to indicate which is larger. Comparators are often used, for example, to check whether an input has reached some predetermined value. On screen, we have the circuit diagram of our light detecting comparator circuit project. It mainly consists of two parts, the comparator circuit and a common emitter bipolar junction transistor circuit, which acts as a switch that turns a DC fan on or off. And to further discuss each component and its function, we have Mika Manalili.
Beginning with the comparator circuit itself, excluding the 12-volt DC input, we have 5 main components. An LM358 op-amp, 2 10 kΩ carbon film resistors, a 15 kΩ resistor, and a light-dependent resistor. One of the 10 kΩ resistors along with the 15 kΩ resistor respectively serves as R1 and R2 in the circuit. This setup creates a voltage divider, and the voltage across R2 serves as the reference voltage of the circuit, which is connected to the inverting input of the op-amp at pin 6. This voltage will not change throughout the whole duration that the device is turned on. That is why it serves as the reference. Another voltage divider is created with the other 10 kΩ resistor, which is the R3, and the light-dependent resistor, which is the R4. This voltage divider is connected to the non-inverting input of the op-amp at pin 5, wherein the voltage across R3 is compared to the reference voltage to determine whether the output should be 1 or 0, or in this case, Vcc or the ground. The voltage across R3 can vary because depending on the presence of the light, the resistance of the light-dependent resistor R4 will change. According to electronics4u.com, an LDR or light-dependent resistor, as the name states, is a special type of resistor that works on the photoconductivity principle, which means that resistance changes according to the intensity of light. Its resistance decreases within an increase in the intensity of light. And last but not least, the LM358, which serves as the comparator. As seen in the figure, this integrated circuit or IC actually consists of 2 amps, either of which can be used. In our case, pins 1, 2, and 3 were defective. That is why we used pin 5 and 6 for the inverting and non-inverting inputs, pin 7 for the output, while pin 8 for Vcc and pin 4 for the ground. When the signal at non-inverting input is higher than the reference voltage, the output is equal to Vcc, which is 12 volts, or closer to 11 volts, considering some of the signal is consumed by the circuit. Otherwise, if the reference is higher, the output is 0 volts or ground. As for the BJT circuit, it only has 4 main components: a 2N222 BJT, a 5.6 kilo ohm base resistor, a 1N4001 diode, and a 12 volts DC fan. According to monolithicpower.com, a bipolar junction transistor or BJT is a semiconductor device that consists of 3 layers and 3 terminals, with alternating P-type and N-type layers. The 3 terminals are the emitter, base, and collector. BJTs exhibit 3 distinct modes of operation, namely cut-off, active, and saturation, which are determined by biasing conditions of the junctions. In the active mode, the base emitter junction or BEJ is forward biased, while the collector base junction CBJ is reverse biased, causing the BJT to function as an amplifier. In the cutoff mode, both CBJ and BEJ are reverse biased, resulting in the BJT being turned off. And in the saturation mode, both the BEJ and CBJ are forward biased, leading to the BJT acting as closed switch, with the base current being sufficiently high to cause the collector emitter voltage to be low. The 2N222 BJT in this case act as a switch operating in either the cutoff or the saturation region. The 5.6 kilo ohm base resistor, where the input signal is being applied, ensures that the DC fan can reach its saturation. While at the collector terminal, the 1N4001 diode acts as a safety component which prevents the DC fan from being damaged in case of short circuits. And receiving the output of the entire circuit, also at the collector terminal, the 12-volt DC fan turns on when there is sufficient signal being applied to the BJT circuit and off if not. Moving forward, Michelle Pexon will discuss the calculation of the values of the resistance and the induced voltage of the light detecting comparator circuit.
Calculating resistance values and induced voltages of the comparator circuit. This process actually involved more trial and error on our part compared to actual solving. However, to simplify the process, first, we measured the resistance of the light-dependent resistor when there is light present and also when there is no light present. When there is intense light, the LDR has a resistance of 3 kilo ohms. When there is no light, the LDR has a resistance of 30 kilo ohms. Then, we also fixed the value of R3 to 10 kilo ohms to simplify the process. With these values set in place, first we have the value of the non-inverting input with the lights on. Looking at the voltage divider formula, we have Vin is equal to the voltage across R3, which is equal to the total voltage, which is 12 volts, multiplied by the value of R3, 10 kilo ohms, divided by the total resistance, which is 10 kilo ohms, plus the resistance of the LDR when the lights are on, which is 3 kilo ohms. This leads to the non-inverting input being equal to 9.23 volts when the lights are on. Then, using the same given values, when the lights are off, the non-inverting input is equal to the voltage across R3, which is equals to, once again, 12 volts multiplied by 10 kilo ohms, but this time it is divided by 10 kilo ohms plus the resistance of the light-dependent resistor when the lights are off, which is 30 kilo ohms. This leads to the non-inverting input to be equal to 3 volts when the lights are off, with the extreme values being 9 volts and 9.23 volts, whose median is roughly around 6 volts. It would be safe to assume that this value can serve as the reference voltage. However, upon testing the comparator circuit with these given values,
Under a real-life setting, it was difficult for the non-inverting input to go below this value. Therefore, we increased it using a higher resistance for R2 compared to R1. So instead of two resistors with the same value, which would have divided the VCC in half, leading to a reference voltage of 6 volts, we use 10 kilo ohms and 15 kilo ohms for R1 and R2 respectively. Then, using the voltage divider formula, we have the reference voltage is equal to the voltage across R2, which is equal to the total voltage multiplied by R2 divided by the total resistance, which is 12 volts times 15 kilo ohms divided by 10 kilo ohms plus 15 kilo ohms. This results to a reference voltage of 7.2 volts. Recall that the comparator compares the signal applied to the non-inverting input to the reference voltage in the inverting input. With this in mind, we will now determine the output when the lights are on and when the lights are off. So when the lights are on, the non-inverting input is greater than the reference voltage. That is why the output is ideally 12 volts because the VCC is equal to 12 volts. However, taking into account the voltage loss because of the signal consumed by the components itself, the real-life value of the output voltage should be closer to 11 volts. On the other hand, when the lights are off, the value of the non-inverting input is lower than the reference voltage. That is why the output is equal to 0 volts or ground. Moving on to calculating the resistance of the resistor at the base terminal of the BJT switching circuit, the following values are given. IC sat of the DC fan is 0.29 amperes. The measured beta of the 2N2222 BJT is 188, and the measured output voltage of the comparator is 10.6 volts. In the computation, we will be using the real values to achieve accurate results. The first step is to solve for the base saturation current, which is equal to IC sat divided by beta. This is 290 milliamperes divided by 188, which is equal to 1.54 milliamperes. Then, using the Kirchhoff's voltage law, we have RB is equal to the input voltage or the output of the comparator, which is denoted here as V2, minus VBE divided by IB sat. 10.6 minus 0.7 volts divided by 1.54 milliamperes, which is equal to 6.428 kilo ohms. However, a resistor with the exact resistance value was not present, therefore we used the next lower resistance value resistor, which is 5.6 kilo ohms. This is to ensure that it is easier for the circuit to reach IC sat. Note that if the collector current saturates, VCE is equal to 0 volts, which is a virtual short circuit, and Vout is equal to VCC, which is 12 volts. Therefore, the circuit is on. While if the IC does not saturate, VCE is equal to VCC, which is 12 volts, and Vout is 0 volts, meaning the BJT switch is turned off. In the video, we can see the actual values of the induced voltages across the circuit. First, we have the reference voltage, which is 7.21 volts. And the non-inverting input is 5.58 volts, meaning that the comparator circuit is turned off because it is not exposed to light, effectively leading to an output voltage of only 2.1 millivolts, in which case the BJT should also be turned off. As proof, we can see that VCE is equal to 11.4 volts, which is closer to the 12 volt VCC instead of 0, meaning that the BJT is off. Then, when the lights were turned on, the value of the reference voltage was measured to be around 4.47 volts, which is lower than expected. But what is important is that the non-inverting input should be higher than this value, which, as we can see, is at around 5.3 volts, meaning that the comparator circuit is on. The output voltage is also lower than expected, which is at around 6.2 volts. These lower values may be caused by signal fluctuations or component loading. However, we can still effectively see that the comparator works properly because it produces an output voltage when the lights are turned on. And again, as proof, as we can see here, VCE is equal to around 567.6 millivolts. Therefore, the switch is turned on.